Hello everyone. In this video, we'll try to understand what is vertex cover problem, as well as we'll try to understand what is the definition of NP hard and how to prove that vertex cover problem is NP hard problem. So before we go into the details of vertex cover, let us try to understand what is NP hard. So if any given problem or a language is to be classified as NP hard, here M is the language or the problem which is to be classified as NP hard, then it is first necessary to find out a language L or problem L which is classified as NP. It means that you will have to find out some particular problem L which is already classified as NP. And if it is possible to perform the reduction of L to M in polynomial time, then we can prove this M as NP hard. So it's a basically a reduction logic here. Any problem M to be proved as NP hard, first find out a problem L which is already proved as NP, and then just transform or just map or just reduce this L to M. How to prove a given problem is NP, that is also we have discussed. NP is nothing but non-deterministic polynomial. So if any given problem requires very large time for generating the solution, but a fixed polynomial time for verification, then that problem is called as NP problem. For example, if you say traveling salesman's problem, then finding out the solution for traveling salesman's problem is very large time, but proving that will be always in order of n. That is, once you generated the solution, if you want to prove whether your solution is correct or not, this verification can be done in order of n time. So this is called as NP. And if a problem NP can be reduced to any given problem which is to be proved as NP hard, then this reduction should happen in polynomial time. And if this transformation happens, then M is called as NP hard. So this is the reduction from the problem X to problem Y. Now let us try to understand what is vertex cover problem and why vertex cover problem is, first of all, we can say why cover problem is NP. So first understand what is vertex cover problem. Vertex cover problem is nothing but it is set of vertices of a graph which covers all the edges present in that graph. That is, a vertex cover is nothing but it is set as which represents the vertices which covers all the edges of the graph. Covers means the edges of the graph are incident on this vertices. For example, if I have something like this A, B, C, D, okay, then I can say that the vertex cover of this particular graph is all the vertices which covers the edges A, B, C, D. Suppose I take A, and then if I take A, it will cover these two edges, and if I take D, then it will, if I take C, then it will cover these two edges. So vertex cover for this graph is AC. So logically, it is the set of vertices on which all the edges are dependent. So why it is NP? Because finding such set is basically again time consuming. But once you find that set, okay, if you can prove that set is correct in polynomial time, then that particular problem will be called as NP. So finding the set is very troublesome, difficult, but proving whether that set is correct or not, then it is very simple to. For example, if I add a age here, and now I want to prove whether AC is a vertex cover, then you can see that AC does not cover the age BD. So this proof does not require more time, or this proof is basically happening in polynomial time. So that's why vertex cover is called as NP. So verification is nothing but verify if all edges present in the graph are incident on what selected vertices. So in how much time it will happen? It will happen in time order of E. So this is a simple example. If vertex cover is ABC, then if the edge is AD, it is satisfying the condition because A is there in the vertex cover. But if the edge is XY, then it will not satisfy because XY is not there in the vertex cover. So vertex cover represents the set of vertices which will be basically controlling or which will be basically used for covering all the edges of the graph. Let us try to understand it through one simple example. So we want to prove whether vertex cover is NP hard problem or not. But before that, let us try to understand it through one simple example. You can see here there is a graph, and if you want to see, if you want to find out which vertices are basically covering all the edges, then we can say A, C, D, and F covers what? All the edges of graph. Suppose you say A, it covers this edge, C covers these two edges, D covers these two edges, C also covers this, and E covers this particular edge. So the vertex cover for this graph is A, then followed by C, followed by D, and followed by F. We are not basically talking about optimized vertex cover here. So we are just talking about plain vertex cover. So how to prove vertex cover is NP hard? It is very simple. Select a problem which is already proven NP. Any particular problem which is proved as NP. Perform the polynomial time reduction of proven NP problem to the vertex cover problem. So if you can perform the reduction of proven NP problem to vertex cover, then vertex cover will be declared as NP hard problem. For example, already we have proved click is an NP problem if it is reduced to vertex cover in what? Polynomial time, then vertex cover can be considered as NP hard problem. So let us try to understand how this transformation happens. And for this particular logic, so this logic is basically divided into two parts. One is we want to do some reduction, and then we want to also prove that hypothesis used in reduction is correct. So reduction can happen in different ways. One way is component reduction and another way is complement reduction. So here we are trying to basically check like what how we can basically generate some hypothesis which will be proved for vertex cover problem using click solution. So if this is a graph of 6 vertices, first step is to find out a click of size k. For example, if I take something like this here, then this, this, and these two. So this is a click of k vertices where k is equal to 4, right? What is click? Click is a part of graph which is complete in nature. So here you can see that there is a part of this graph is complete in nature as well as it has some size k equal to 4. Total number of vertices in this graph is equal to 6. Now what we are doing here is we are trying to convert this graph convert this graph g equal to v comma e into a complement graph which is g equal to v comma e bar. What is complement graph? Complement graph is a graph in which the number of vertices of the given graph will be as it is. For example, if G has V vertices, then the complement graph G dash will also have V vertices. but the ages will be complemented. If G has age E, then G dash will have E bar. It means that the age which is present here will not be present here, and vice versa. For example, if there is, you can see here, there is an age between U and V. So this age will not be there in the complement graph. And there is no age between V and W. So this age will be there in the complement graph. So let me draw a complement graph for you. This is Z, U, then V, then W, and then Y, and then X. So find out a age which is not there in graph, this graph. So VW is not there, so draw this. Clear? Z to Y is not there, so draw Z to Y. Okay. Similarly, what you will observe that WX is not connected, so draw WX. Okay. Similarly, so if you see Y is connected to X, Y is connected to W, Y is connected to V, Y is connected to U, but not connected to Z. Similarly, U is not connected to W. So U is not connected to W. So we can draw this edge also, right? This U is not connected to W. Okay. And what? For example, here, so this is, and also we can say V and Z are also not connected. So this can be also one edge. Okay. V and Z, right? So now what you observe here is we are drawing all the edges which are not present in this graph. V and Z, U and W, W and X, YW is not drawn, ZW is not drawn, ZV is drawn, ZX is not drawn, ZY is drawn because the idea is to add the edge which is not there. Is it clear? So it means that this vertices remain same and the edges are complemented. Now if you find out here, if I find out in this graph, you will find the vertex cover is nothing but it is Z and W. That is the vertices which holds all the edges. So Z holds these two edges and W holds these three edges. It is nothing but if I have V vertices and if I have K vertex click in that V vertex graph, then I will be having V minus K vertex as vertex cover in its complement graph. So this is a reduction which we are trying to prove through the hypothesis. That is, given a graph G, you can convert this graph G into G bar, which is complement. If there is a vertex, if there is a click of size K in this graph G, then there will be a vertex cover of size V minus K in this graph G bar. Again, I am trying to repeat this. G and G bar are basically complement graphs. If there is a click of K in G, then there will be a vertex cover of V minus K in G bar. This way, you prove that vertex cover is what? NP hard problem. What were the steps? First step is check the standard problem proved as NP. Second step is perform reduction using certain hypothesis and then prove that that hypothesis is correct. What hypothesis we have used here is the hypothesis related to complement graph. I hope you understood this and we will be adding few more things in the coming video. So keep watching. Thank you very much.